Welcome to our second lecture on equilibrium. Again, remember we're talking about, it's a matter of balance. In chemical equilibrium, we're talking about balance of rates, equality of rates, a reaction that goes forward and backwards. And when it gets to the same rate, then the concentrations will become constant and we'll have equilibrium. Let's look closely at this reaction. We saw it in our last video. This is the equilibrium between hydrogen gas and iodine gas to make hydrogen iodide gas. The data in this table is from 445 degrees Celsius. Now let's notice when we begin with a half a mole of iodine and half a mole of hydrogen and half a mole of iodine per liter. At the equilibrium point, the concentrations are 0.11, 0.11, and 0.78. When we form the equilibrium constant, let's notice that's going to be the concentration of Hi squared divided by the concentration of H2 and the concentration of I2. When we put those equilibrium values in, we get an equilibrium constant value of 50. In the second reaction, we began with only Hi and let it decompose, so going from right to left. Notice here at equilibrium, H2 and I2 are both 0.055 and Hi has been reduced to 0.39. When we do the math again, look, the same value for the constant. In the third row, we begin with equal amounts of all three gases, both the reactants and the product. Now notice when at equilibrium, 0.165 H2, 0.165 I2, and 1.17 Hi. We throw them into the equilibrium constant expression, and once more. Okay, 50. So our equilibrium constant at this temperature has a value of 50. We've seen that. Let's look one more time. If we look at 1 molar H2 and half molar I2, when it equilibrates, we've got 0.53 moles of H2 left, 0.033 moles of I2 left, and that yields 0.934 moles per liter of Hi. And when we do the math one more time, it comes to an equilibrium constant value of 50. So we see here, what do we see? No matter where we start, we're going to the same place. Remember, that's what the equilibrium constant is telling us. Where will we end up? What is that point of balance? We want to look now at what is called a RICE, or an ICE table. Tro calls it ICE. I learned it as RICE. The RICE table, it's a systematic method to determine and to use equilibrium constants, the KEQs. The table has 4 rows: reaction, initial conditions, change, and then the equilibrium conditions. And again, the first letters spell the word RICE. Here's an example problem. Carbon monoxide and hydrogen gases, when they react, can form methanol, CH3OH. So here's our equilibrium, so we write that reaction. Now, in this particular case, we were just told what the chemicals were, and you get to write and to balance the equation. On our exams, I will give you the balanced equilibrium, but here as we're practicing, let's do it from scratch. So we've got carbon monoxide plus H2 gives me CH3OH. If we look, there's one carbon on either side, there's one oxygen on either side. And to get the hydrogens balanced, we need 2 moles of hydrogen. The second step is to write the initial conditions. Well, the problem statement says we started with 0.5 atmospheres of CO and 1 atmosphere of H2. So those are given. We do not have any product initially present in this example. We now write the change row and the equilibrium rows. So here we are. Here's the full table. We have our reaction. We have the initial conditions. We don't know what our change is yet, but we know one other piece of information from the original problem statement. Says the equilibrium pressure of CO was found to be 0.15 atmospheres. So we've written that down here at the end. Here's the table again, and now we've included the change row. Notice the problem statement says we initially have 0.5 moles, 0.5 atmospheres of CO, and the equilibrium pressure of CO was 0.15. So that means the CO pressure dropped from 0.5 to 0.15, or a change of negative 0.35 atmospheres. So the CO pressure dropped by 0.35 atmospheres. Now, since there are 2 hydrogens for every carbon monoxide, the change in hydrogen pressure is going to be twice as big. There's 1 mole of methanol for 1 mole of CO, so that change is going to be the same. Notice again, my mole-to-mole ratios are 1 to 2 to 1, and my change row, because the change row is the stoichiometry, is 1 to 2 to 1. Let me say that again. Because the stoichiometry of the reaction is 1 mole of CO reacts with 2 moles of H2 to make 1 mole of methanol, whatever change CO undergoes, H2 undergoes twice as much because the ratio is 2H2 to 1 CO. Whatever change CO undergoes, CH3OH, methanol, undergoes the same change because it's a 1 to 1 mole ratio. Our 5th step is to do the column math. Notice here, we had this information on the last slide. We started with 1, and the change was 2 times 0.35, negative, because we're losing reactants to make products. When you do that math, 2 times 0.35 is 0.7. So 1 minus 0.7 is 0.3. For methanol, 0 plus 0.35 is 0.35. So now we have all 3 equilibrium pressures. Again, when we're calculating in a column, we're just doing addition and subtraction. And I've shown it there, and we've got it here in the text as well. Then finally, we use those equilibrium values to calculate our desired quantity. In this case, we want to calculate Kp. I've just written Keq there. We could have also have written Kp because these are pressures. It's a pressure-based equilibrium constant. So looking at our equilibrium, it's going to be products, pressure of CH3OH to the first power, divided by the pressure of CO, times the pressure of H2 squared, because again the coefficient on hydrogen is a 2. So we plug those values in, 0.35 divided by 0.15 times 0.3 squared, and we get 25.93, or rounding back to 2 places, 26. So we can say then that Kp is 26. The equilibrium constants, as we write them, will have no units. There are no units on our equilibrium constants. We simply know that if we calculate or use a concentration, it will be in moles per liter, and the pressure of a species will be in atmospheres. Let's work a second problem. Here's another equilibrium. Methane, CH4, will thermally decompose, that just means if we heat it, it falls apart, to form ethene, and pardon me, that's a typo, that should be ethine, and hydrogen gas by the reaction below. If a reaction vessel is initially filled with 0.115 atmospheres CH4 and allowed to equilibrate, the equilibrium pressure of ethine, C2H2, was found to be 0.035. And we're asked to calculate Kp for this reaction. So once again, here's my reaction. My initial conditions were that I have 0.115 atmospheres of CH4. Here's those same 2 rows again. We'll calculate the change row in just a moment. We know one other piece of information from the problem statement, and that's that the equilibrium pressure of C2H2 is 0.035. Here's that information again, the reaction, the initial conditions, and that one equilibrium condition. Notice now that we can calculate this column. We can assign the elements of the change row because we know that if C2H2 went from 0 to 0.035, it had to increase by 0.035. Now, because 3 hydrogens are produced for 1 C2H2, the change element for CH2 is 3 times 0.035. The coefficient on CH4, it's a 2 to 1 to 3 ratio. This is 2 times 0.035. Notice again, my change row is always going to be in stoichiometric ratio. In this case, 2 to 1 to 3. And so my change row elements are 2 to 1 to 3 times 0.035. When we do the rest of the column math, 0.115 minus 2 times 0.035 gives an equilibrium pressure of CH4 of 0.045. For ethine, we already knew it was 0.035, and 3 times 0.035 plus 0 is 0.105. And again, remind you again, when we're calculating in a column, the mathematics is just addition and subtraction. So we notice again at this point that we have all 3 of our equilibrium values. We form our equilibrium constant so that we can then calculate our desired quantity. So it's the pressure of C2H2 to the first power, its coefficient is 1, times the pressure of H2 cubed, because the coefficient is 3, divided by the pressure of CH4 squared, because CH4's coefficient is 2. When we do that math, you get 2 times 10 to the minus second, or writing that as a decimal fraction, 0.020. Now let's notice that in this particular reaction, the equilibrium constant was relatively small, letting us know that not much reaction occurred, or noting more commonly, that the ratio of products to reactants in general was small. The next topic that we want to talk about in equilibrium is the idea of which direction will our reaction go? If we start with a particular set of conditions, will the reaction move to the right toward products, or will it move to the left toward reactants? And what we're going to do is use what is called Q, the reaction quotient. This reaction quotient Q takes the same form as KEQ, KP or KC, KEQ, but it uses present values to calculate it rather than the equilibrium values that KEQ uses. So the equilibrium constant tells us where the reaction will end. Where will it find balance? Q, the reaction quotient, tells us where the reaction is now. Not where it's going to be, but where it is now. And we're going to find that there is a simple mathematical relationship that corresponds to what we see in a simple physical system. Let's consider this simple physical system right here. I've got a valley. And I know that if I put a ball in the valley, this is the equilibrium position. That's where the ball is going to end, at the bottom of the valley. Now, if I have the ball to the left of that equilibrium position, the ball is going to roll to the right to get to equilibrium. If the ball is on the right of the system, it's going to move to the left to go where? To the equilibrium position. Notice it doesn't matter whether I start from the left or the right. I'm going to go to that same equilibrium position. It's just like that data that we looked at the first of this lecture where the equilibrium constant was constant. It tells me where is the reaction going. The reaction quotient Q, because it takes the same form, is that ratio of products to reactants. And so what we see is that the value of Q relates to KEQ just like the balls do here as they roll down in the valley. If Q is to the left of KEQ, so here Q is less than KEQ, and the reaction is then going to run to the right to make more products, and to make that ratio Q turn into the value of K. On the other hand, if Q is greater than K, if we're to the right of K, then the reaction is going to run to the left to reduce that ratio of products reactants from a high value Q to what would be the lower value of KEQ, because Q started out greater than KEQ. Here in text is exactly what we're looking at. If Q is less than K, so it's to the left on a number line, the reaction moves to the right. If Q is greater than K, then it moves to the left. If we just happen to hit it, if Q equals K, then we're at equilibrium and the reaction is not going to go anywhere. Let's look at an example. Let's go back one more time to our equilibrium between H2 and I2 to make 2HI. Now at 500 degrees Kelvin, this has a Kp value of 81.9. The question then asks, if I begin with 0.2 atmospheres of I2, 0.1 atmospheres of H2, and 0.5 atmospheres of HI, in which direction will this reaction proceed? Will it go to the right to make more products, HI, or will it go to the left to yield more reactants so that the pressures of I2 and H2 would increase? Well, here is Q. Now notice that Q is formed just like K. Look, it's products over reactants. It's products over reactants, just like it is every time. We were given the data in pressures, so we've got them here as pressures. So Q is going to be the pressure of HI squared divided by the pressure of I2 times the pressure of H2. And when we put our present values in, we get a value of Q of 12.5. That's much less than 81.9, which is our KEQ value, Kp. And so we find that this reaction is going to proceed to the right. The pressure of HI will increase, and the pressures of I2 and H2 will decrease. That means in this fraction right here, this number is getting bigger, these numbers are getting smaller, so this ratio that is presently 12.5 will increase until it reaches the equilibrium value of 81.9. The last thing we want to do in our video today, in our lecture today, is to talk about how to use KEQ to find equilibrium concentrations. These type of calculations will come in a couple of different forms, and let's begin with this one. If we are given all but one equilibrium pressure or concentration, we want to find the one that's missing. One more time, here's I2 plus H2 makes 2HI. Kp is 81.9. If the equilibrium pressures are 0.9 I2 and 0.1 H2, what will the pressure of HI be? Well, if we set up our Kp, let's notice Kp is pressure of HI squared divided by the pressure of I2 times the pressure of H2. We know the two on the bottom. We don't know the one on the top. So here we're going to say, all right, so let X equal the pressure of HI. So that means Kp is going to be X squared over 0.9 times 0.1. And that ratio is going to equal 81.9. I'm going to solve this equation for X squared, multiplying both sides by 0.9 and 0.1. And that gives me that X squared is 7.371. I take the square root of both sides and find that the equilibrium pressure of HI is 2.71 atmospheres. Again, we have three species, so we need 3 pressures to calculate KEQ. In this case, we know the value of KP, we know PI2, we know pH2. We solve for that unknown, and we've done so here. The second type of equation, and this is one we're going to do 2 examples of this one because this is a very, very important thing for us to be able to do. Given a set of initial conditions and the value of KEQ, calculate the final or the equilibrium values for those species. Here again, I2 plus H2 in equilibrium 2HI, a Kp of 81.9. I've gone ahead and written the Rice table out in its entirety. Let's talk our way through it. Here's my reaction. That was given to us. Let's read the rest of the problem statement. If the system initially contains only 0.5 atmospheres of I2 and 0.5 atmospheres of H2, so there are our initial conditions, find the equilibrium pressures of all 3 gases. Notice, we didn't start with any HI, so its initial value is 0. Being good algebra students, let's define X. Let X be the pressure of I2 that reacts. So that means the change for I2 is going to be negative X. The change for H2 is going to be negative X because that's a 1-to-1 ratio. The change for HI is going to be a positive 2X because my coefficients are 1-to-1 to 2. And my change row is always in stoichiometric ratio. So then I can do my column math. 0.5 minus X is 0.5 minus X. 0.5 minus X is 0.5 minus X. And 0 plus 2X is 2X. We then can set up our Kp. There it is, products over reactants, and put those values from our change table on the last, from our Rice table on the last page. Put it in. The pressure of I2 was 2X, so that's 2X squared. Pressure of I2 was 0.5 minus X. Pressure of H2 was 0.5 minus X, and that's going to equal 81.9. Now, if we look at this, this is going to yield a quadratic equation. So we can do all of the algebra and find the quadratic formula, and then use the quadratic equation, and then use the quadratic formula to solve it. In this case, however, when we look, we note that the left-hand side of the equation is a perfect square. 2x quantity squared divided by 0.5 minus x quantity squared. So I can simply take the square root of both sides. So the square root of the left side is going to be 2x divided by 0.5 minus x. The square root of 81.9 is 9.050. I then have the simpler equation, and I can solve that algebraically. Multiply both sides by 0.5 minus x. Carry 9.05 times 0.5 is 4.525. 9.05 times negative x is negative 9.050x. Then bring that over to the left-hand side. Add 9.05x to both sides, so I get 11.05x is equal to 4.525. Dividing both sides by 11.05 gives me an x value of 0.4095. So that means that the pressure of HI, which is 2x, is going to be twice that value, or 0.819 atmospheres. The pressure of I2 and H2 are each going to be 0.5 minus x, which turn out to be 0.0905 atmospheres. Here's a second example of doing the same type of problem. This one we will set up and talk about solving the quadratic formula. In this case, we have a reaction between CH3OH, acetaldehyde, carbon monoxide, and methane. Again, here we're given initial conditions. If the system initially contains only acetaldehyde at 1 atmosphere, we want to find the equilibrium pressures of all 3 gases. Here's my reaction. That was given. Here are my initial conditions. They were given. 1 atmosphere of my reactant, no product. We're going to let X be the pressure of the acetaldehyde that reacts, so that change is negative X. Because it's a 1 to 1 to 1 ratio, this row is just going to be X, X, and X. It's negative for the reactants. It's positive for the products. These pressures can't be less than 0, so they must increase, and that means this reaction is going to shift, is going to run to the right. At equilibrium, 1 minus X is 1 minus X, 0 plus X is X, 0 plus X is X. Again, one more time, the column math is found by doing the addition and subtraction. We then can plug those variables, X, X, and 1 minus X, into our Kp expression, products over reactants, always. Products over reactants, whether that's concentrations or in this case pressures. And the problem statement told us that Kp was 105. So here's the equation one more time. Kp is then going to be X squared divided by 1 minus X is equal to 105. I'm going to multiply both sides by 1 minus X. That's going to give me that X squared is equal to 105 minus 105X. And I can rearrange that and put it in standard quadratic form. X squared plus 105X minus 105 is equal to 0. Here's a standard quadratic form. AX squared plus BX plus C is equal to 0. And so we can see here that A is equal to 1. That's the coefficient on X squared. B is 105. That's the coefficient on X. And C is negative 105 because I'm going to add C, so I'm going to add a negative 105. There's our good friend, the quadratic formula. Now, many, if not most of you, do not have the quadratic formula memorized. Please know that I will provide that formula for you. Let me take this moment here to talk about what our exams are going to look like briefly. We're going to be taking the exams as a quiz in the context of the Moodle page. You will also have access before the exam to a downloadable sheet of formulas and the periodic table. You can print those out, or you can have them up in a separate window. Obviously, you're not going to have anything else available to you, but I will provide you with all of the relevant formulas and a periodic table. Clearly, you've got to have the periodic table if we're doing chemistry. Now, if we plug A, B, and C into the quadratic formula and solve, you will find that the two values of X are negative 106 and positive 0.991. We can throw out that negative value because we know that this pressure, it can't be a negative value. X can't be negative because we can't have a negative pressure. We can't hit the walls a negative number of times. So we would have a negative pressure of all three species, and that simply would not work for us. So choosing the positive value of X then gives me then that the pressure of CH3CHO is 0.009 atmospheres, and the pressure of CO and CH4 are 0.991 atmospheres. Now, there are a lot of places for us to have made minor math errors. The beauty of this particular method and the beauty of using equilibrium constants is that we can now take these calculated values and ask ourselves, did the numbers that we get, is the pressure of CO times the pressure of CH4 divided by the pressure of CH3CHO, is that equal to 105? Let's move over here to the left-hand side of the board and simply do the math. The pressure of CO was found to be 0.991. Pressure of CH4 also 0.991. And the pressure of CH3CHO was found to be 0.009. When you plug those into your calculator, you're going to get 109. And the question then, is 109 equal to 105? Exactly? No. Approximately? Yes. We talked about in the last video that there's always going to be some round off error. Anytime we do more than one calculation in a row, we're going to find some round off error, and that's what the case is here. The difference here between our back calculated number 109 and our starting number 105 is less than a 4% error, and so we're going to argue this is close enough. That concludes our second video on equilibrium. I'll be back with you tomorrow with one more video talking about calculating dynamic equilibria.